All right. Good afternoon, everyone. Oh, okay, now it's recording. Okay, good afternoon, everyone. So, I promised that we would settled we'd do the tablet this week, and so that I could show you with the drawing with the pen. But unfortunately, it's not charged, and it's not charging for some reason. Technical difficulties. So what I'm going to try to do is I'm going to try to show through the Microsoft whiteboard on this computer and see if that works out for me. I'm hoping this works, because what I wanted to show you was kind of how some of these different what are they called? Some of these different data structures, how they work. Okay, so what you should be seeing now is this Microsoft whiteboard. All right, so let's just talk about arrays, kind of the array list type of data structure, and then we will also talk about the list data structure, and then that way you could kind of see how the well, I guess we could also mention the set as well, but let's go to the basic one, the array. Okay, so the array and the array list. And remember, the array list basically is just its underlying data structure is an array. And remember, the way the arrays are structured are, if it'll let me draw, okay, good. Okay, is you have, okay, is you have these different array memory locations. Okay, and when we're indexing them by 0, 1, 2, 3, 4, 5, and so forth, right? Okay. Now, the way this works in memory is that these are what's called contiguous memory locations. And so what happens is we put a value here. Now, it could be a primitive type like an integer or a double or a float or whatever. But more often than not, we're probably putting something in there that's it could be an object, like a string, or an object that we created, like in our assignments, for example. You might create an array list of students or an array list of courses or something like that. So here's the thing. So we put different things into our different positions. So I'm going to change up colors here so that we can see some stuff. So here we have, value 1. Whatever value 1 is goes into index 0. We'll call it actually V0 to be consistent. Okay. And then V1, and then V2, and then we might not have anything on these other ones as well. Now, when we want to add a new value to our array list, it gets put into this last position. Pretty easy, pretty straightforward, just to add a new value to the end, boom, it gets put in there, right? But what if we want to, I'm going to go ahead and put that in there. But what if we wanted to insert a new value into our array list or our array? Well, what has to happen is that all of these different things, change that, then has to get moved, right? So let's say we want to put something into this position. Well, we got to take this and move it over here. Then we have to take this and move it here. You have to take this and move it here. And then we can put whatever our new value is right there. Right? So that's extra work that has to be done by the algorithm. And I think this is important, actually, that I'm starting off the efficient algorithms discussion with this whole set list performance discussion. All right, because how it works out. So we had to move all this stuff over, but so that means that inserting a new value into our array or array list is going to be time consuming, right? It's going to take a long time because we have to move everything over. In the same way, if we wanted to remove a value, let's say we wanted to remove this value from our array list, right? Remove this guy, then we'd have to move this into here, right? Move this into here, then move this into here, and then move this into here, and then remove this into here. Okay, so any type of modification is going to take up a lot of time. It's going to take up a lot of extra time to make stuff happen. But to access an individual element, what happens? it becomes very easy, right? If I wanted to get whatever was in position 3, index 3, for example, I just get it. It's just there. I just go and grab it. I don't have to navigate anywhere. I just say what we call the offset for memory locations, and you'll learn all about this in your digital logic class. And if you ever take a computer architecture class, they'll cover that in there as well. But it's very interesting that you just go out there, you grab the third thing, right? You add this offset to the base memory spot, you go and grab what's in that memory location, you're done. You don't have to go looking through other stuff to get there. Okay, index-based obtaining things. Okay, so now let's talk about the way the linked list works. So the linked list, instead of being an array, or sorry, a set of contiguous memory locations, what we do is we have this thing that's called a linked list node. Okay, and what we put into this node is we put whatever the value is that we are holding there. Okay, and then we have this pointer that points to a new element in the list. Okay, so if this is the end of our list, let's say this is the end of our list, it's only one value, this points to this points to null. Okay, so if we've hit something that points to null, guess what? We're at the end of the list. We're done. Okay. If what our pointer points to is another node in our list, then we're not at the end yet. Okay. There's also a special value that what happens is there's a thing that's called the head that points to the first element in our list. Okay. So let's go ahead and put a few more. I don't want to put a ton, but let's go ahead and put a few more nodes in our list. Okay. And let's leave it at, let's go ahead and go one more. Sure, why not? Let's go crazy and have like 4. All right. And so, and then what does this point to? What does this point to, guys? If this is the end of our list, this is the last one. Right, no, exactly. All right. So we'll put this V1, V2, V3. Okay, my handwriting's terrible. This is why I wanted my tablet. All right. So what we're going to see is that what if I wanted to insert this new value into my list? Well, I don't have to move anything. All I have to do is, okay, I'm going to create a new node here. We're going to give it our value, v sub n we'll call it. And here's what we do. We create our new node. And let's say I want to insert it right here. This is where I want it to be, is right there. Okay. Then what I do is I say, okay, what is this, the node that I want to put it immediately after, what does it point at? What does it point to? And I say, make this point there. Okay. It's very important that this is done in this order, by the way, because I'll show you what happens if we don't do it in the right order. Okay, let me move that over there. All right, I'll show you what happens if we don't do it in the right order in just a second. All right, so we point this to here, and then we take this and say, okay, you no longer point there. We're going to make you point here instead. And we're done. We didn't have to copy this into something else, this into something else, this into something else. All we had to do was change this pointer to be here and this pointer to be here. And we're done. Okay. Now, let me show you why the order is important on this. Okay, good. Because if I point this, if I make this pointer change first, so if I say you're not going to point there anymore, I want you to point here now. Okay, now I have nothing that points to this, so I don't know how do I make this point to that. There's nothing. It doesn't. I can't find it. It's lost. Right. So, by the way, this also makes it is how it becomes very easy to completely delete a linked list. Is you could simply say point the head to null instead, and now the complete list is lost. Okay. All right. So make sure you do this in the right order. Okay. So this one first, then this one. Okay. And again, you'll probably learn all about this in your algorithms and data structures class. Okay. So now the difference is so fast insertion. Okay. Insertion, adding into a list, deleting an item. If I wanted to delete, let's say I wanted to delete this guy here. I want to delete V1. Okay. I want him to go away. Over here, remember, we had to move everything over to delete it, right? But here, guess what? To delete V1, you know what I have to do? If I do this, V1 is deleted. Now you might think, wait a second. V1 still has this pointer to V2. So how can V1 be deleted if it still points to V2? But see, there's no way for me to get to V1, is there? There's no way for me to get to V1 from somewhere else at this point. It's lost. And if you guys remember, we talked about this whole concept of garbage collection, right? That Java does this whole thing with garbage collection. Because nothing points to the node V1, even though V1 points to something else, because nothing points to V1, it's considered garbage, and it will be collected by the garbage collector and done away with. Okay. There's a little bit slightly different wrinkle with this because of the way that Java does linked list, and it actually does it as what's called a doubly linked list, which is a bit outside the scope of this course, and so I don't want to get into it because it's much more important for you to know for your algorithms and data structures course. So, but just wanted to say it. So inserting and deleting, super fast, right? Super fast. But what about searching? So here, remember searching for an array, I just had to go to the offset, get that value, I'm done. I got it. It's fast, right? But here, if I want to get whatever would be considered at index 3, so if we're looking at 1, 0, 1, 2, 3, if I wanted to get what was at index 3, this thing here, I can't just get there, can I? I can't just say, okay, add 3 to 0 and give me what's in that memory location, because this is somewhere, remember, we don't know where it is. We don't have a direct address to this thing in memory. What we have to do is we have to go to the first value in the list and then say that's index 0. Then we have to follow its pointer to the second value in the list and consider that as index 1. Then follow its pointer to the third value in the list and consider it as index 2. Then follow the next value in the list and consider it as index 3, and say that's it. That's the value that we want to have. Okay. So we have to navigate here, 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 here to get to this value in the linked list. Okay. So inserting, deleting super fast. Here, finding much harder and much slower. Okay. And so I won't go too much into the set stuff, but I do want to go ahead and pull up this set list performance example, because I think it's a very interesting example of how to do this. So let's see, what do I have? Wait, hold on. I have list as an array list. I have a hash set, a linked hash set, a tree set. A linked list and array list. Okay. Okay. All right, so I'm going to share this on the screen. So you guys can see it. All right. Okay, so in this example for this set list performance, we did talk a little bit about hash sets and how they were done. So the idea of the hash set is we put ourselves into a bin. But actually, I'm just going to go ahead and show this one again because I think it's important that you see it. So when we create this hash set, remember what we do is we kind of, each value that we add, so London in this case, gets a hash value and we put it into that bin. And so when we search for a thing in the set, if you remember here, if two things have the same hash value, basically it becomes like a linked list that comes off of that hash set. Okay, so basically when we go to try to find a value, if we were to try to find London or Paris or New York or whatever, then what would happen is that first the hash value would be calculated. It would go to that bin and it would look for that. It would look in that linked list for one of these. Okay, so basically what would happen is, let's say I said New York. Okay, New York is this one here. And let's say I said I want to find New York in my set. Does my set contain New York? The hash value would be calculated. It would come to bin 1, and it would look in that linked list for New York. Now, this becomes very fast to search in the set because we only search the bin that we calculate that it should appear in. So if we come to this bin, instead of having to search every value in the set, what we do is we say, okay, does this linked list contain this? We only search the single linked list from this bin. Okay, so it kind of divides our search time into, compared to a regular linked list, it divides our search time by 16, since there's 16 different bins here. If you remember here, there was bins 0 through 15. Okay, all right. I'm assuming you guys can see. You actually can't, can you? Can you see? Okay, are you guys able to see the canvas thing that I have up here that I'm commenting on? Because it looks like it may be in a different window, so I'm not sure if you're able to see it or not. Let's see. Let me take this opportunity to read Arjun's question. Can we say correct for more than one element can refer same? I'm assuming you mean in the linked list. And so if two things can point to the same other thing, that's fine. But if nothing can get to a node, if we don't have any pointer to a node, then it's kind of like when we've shown before, where if you point a variable to an object, and then you take that same variable and you point it to another object instead, and nothing points to that first object, it's just you can't get to it anymore, then the garbage collection cleans that up. Okay, I'm going to assume that all of you, since there's no comments on the Canvas question, that you are able to see this thing over here that I've got that I'm moving around. Whoop, that I'm moving around. Here, this Canvas thing with New York highlighted. Okay. Okay, so let's finish that out. So you would think that set searching could be pretty fast. It might take some time in order to calculate the hash value for an object to figure out where to put it, to figure out which bin to put it in. So that would be something we wouldn't necessarily know right offhand how fast that would be. But we've got to figure that sets searching will be quite quick, right? Because we'll just calculate that hash value, go straight to that bin, and search that bin. Okay, so all that was to say, let's take a look here. Okay. We're going to have an array. We're going to first create a list that of whatever size n, which n will make it 50,000. Okay. And we're just going to add the numbers 0 through 49,999. And then we're going to shuffle it to kind of just mix it all up. Okay. And then we're going to test some different things using some different data structures. We're going to have a hash set like we just looked at. Now we're going to base a hash set on our list. Notice that all values are distinct, so that shouldn't have any problem with that hash set, right? And then for each one we're going to get test time to find each member in the set, and then how much time does it take to remove all members of the set. Okay, so if we look through the get test time and get remove time, test time is basically just saying for each one, for each one 0 through n-1, we're just going to say run the contains method for some integer, some random number times 2 times n. So you guys remember that math.random is going to give me a random number from 0 to 1, not including 1. Multiply it by 2n, so I'm including testing for numbers that aren't in the collection, right? And then convert it to an n. So basically, I'm going to test. I'm not going to necessarily test all values. I'm just going to find out, just randomly come up with integers that range from 0 up to 2n. Okay. Right, and then it's going to tell me, okay, once I've done that n times, I've tested for whatever number 10 times, I'm going to return the current time minus whatever the current time was when I started. So hopefully this would be in, only a few milliseconds for a few of these. Then remove time is I'm just going to remove every value in the collection. Okay. Now, I'm not going to do this randomly this time because it's shuffled. It was shuffled already, and so it was already mixed up. But this is going to have both the search and remove effect, right? Because I'm going to have to both find the value in whatever it is, whatever the collection is, and then I'm going to have to remove it as well. Okay. Yeah. Yeah. Make sure that remove, does remove just remove the first value? Does this remove? No, I can't. Yeah, it removes that value. It looks for that value. Okay. All right. So, question. Here we go. Let's talk through this one. So we're going to do this with a hash set. We're going to do this with a linked hash set, which I'm not going to show you that one. They're going to do that with a tree set. But what I'm really interested to find out is, what do you think is going to be fast? Or which one do you think is going to be more efficient between the array list, the linked list, and that's it. We got array list, linked list, and hash set. Okay. So remember, we're going to test for random values in the hash set or the whatever it is. We're going to remove all values from the set or from the collection. So let me do this. I'm going to comment these two out because we didn't really talk about them too much. But I do want you to tell me, okay, what do you think is going to be the fastest and what do you think is going to be the slowest between the hash set, the array list, and the linked list? Okay. Right, well, they all have the same number of items. They all have 50,000. So we got somebody saying array list is going to be the fastest and linked list is the slowest. Okay. Okay. Hash set is somebody's a couple of different opinions there. Good. Let a few more people answer if you want to think it through, kind of think it through a little bit, and then we'll run the simulation and see. All right, let's take a look. Okay. All right, let's see what happens when we run this thing. First compile because I commented some stuff out. Okay. Oh, and I'm just going to run it instead of running through debug, only because running it in debug may affect how much time each takes. So we're just going to run. Okay, so that was hash set, was pretty fast on both. So array list was pretty slow on test, but not too shabby on remove. It's still working on linked list. Wow, that was a long time. 16 seconds on test time for a linked list. So if I were you, if I were sitting in your shoes or at your desk or whatever it is that wherever it is you're sitting, I would say, wait a second, Hojam. You said that the array list was really fast for finding stuff, and look at that. Look at how slow that is. That's a problem. Something's not right. Something's not right. Well, here's the problem with the finding an element in the array list test here is that we were not finding an index. Okay, the test time was finding if a specific value exists in the array list. Right, and so because we have to search it to find out if that value is in there, we do need to go ahead and go through item by item till we find the value or not, or until we search through the entire thing. Okay. Now, what is interesting about the array list for the remove is that the remove method actually for an array list removes based on index. So it does, or no. It should have done it the other way. No, remove could be there. Yeah, it would remove the index of this. All right. So I wonder if it's going to have all the values in there. Let's see something. Let's see what happens. Let's see what. Actually, I should have done this. Okay, there we go. So I have this list. I created a set. Okay. Okay, let's see something. The set should be empty now. Okay, good. So the set is empty. That's good. I'm wondering about this array list because the array list says that it removes based on index. That's what the why is it taking? All right, let me. Why is this not working? All right, you can't see the canvas. Let me go ahead and try to share it as a screen instead. Share it as the whole window there. All right, let's see if this works now. Oh, shoot. Well, what's going on here? All right, here we go. Now we've got the array list. Now let's see what the list one looks like here. Okay, total node count limit 500. Okay. So we get the. It's taking some time to test things. It's taking longer than I expected it would. Okay, this is. Okay, let's see. Let's try this again. What I want to do. Okay, so yeah, so the array list, okay, that's interesting. The array list still has values in it. So what that, and the reason for that, this didn't exactly do what we thought it was going to do. This is an interesting example that they gave us then. Because the remove method for the array list and for the linked list doesn't remove the value. It removes the index. So basically what it did was it said, okay, it went through the first time through the loop and said remove index 0. Then it said remove index 1, then 2, then 3. The problem was that you actually never got, when it got up to index n, or n minus 1, there was no index n minus 1 anymore. Interesting. It should have gone the other way. It should have gone from n down to 0. That's what we should have done if we want to see a better example of removing every element from the list. So if I come over here, for example, and say step 2, let's see how long it takes. That's our linked list, and list 2. Interesting. List 2, on the other hand, the linked list, does completely get deleted. I wonder how that works. It did remove all the values. Interesting. Huh. Okay, well, that's very interesting. I wonder if it really is removing the values then. But it shouldn't, because it says remove should be based on index. Make sure about that. All right. Okay. It's interesting that it seems to be removing based on value, but the method according to the array list, according to the list interface, should remove based on index. So it doesn't seem to be doing that. It seems to be actually removing the value instead. That's weird. All right. I'll have to take a look at why that is. All right. Okay. One other thing before we take our break, and then we'll get into efficient algorithms. So one example we didn't get to look at earlier was we talked about this this count keywords using a map, right? Or in this case, we're using a hash set to count keywords. Now, the reason we can use a set for this is because we don't care so much how many times the different keywords appear. We don't care how many times the word switch appears, for example, or public or default, or whatever. What we care about is just how many total keywords appear in a file. So let's do this. Let's compile this. Okay. And what we're going to do is we're going to create our own little test file here. We're going to create a new Java file, and we're just going to call it public class my test, and that's it. Okay, that's it. We can compile it. It should work. See, very simple Java file. All right, to compile. And then what we're going to do is we're going to run our count keywords. Okay. So it's going to look and it's going to see the word class in there. It's going to also see the word public in there. All right. Okay. So when we go to run this, it's just going to say, okay, If the set contains the word, we're going to add one to it. So what we're going to do is we're going to get, when we run this, we're going to say, look in my test.java. Oh. You should exist. You're right there. Could it be the package is the problem? But that shouldn't matter. Why? Why does it not like me? Why does it not like the... Wonder if it's looking in a specific folder. Let's try this. Let's try taking the package out. There we go. Okay. Weird. It needed to be in a package. That's weird. Okay. All right. So it looks in that mytest.java, and what did it find? It found package, public, and class. So basically, anytime that a purple word appeared is what it was going to count. Now, the reason again that we can use the set interface here is because we can take our list of keywords and we can say we can make it as a set, because we don't care how many, we're not counting how many times the word public appears. We're counting how many times any of these words appear. And you know, the cool thing is we can use this on our own file, right? So let's look. Okay, how many purple keywords do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Don't forget if. 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. So if we can run this on our own file here. Okay. 24. Wait, what? I counted 22. Did I count wrong? What do you think's going on? Why did 24? I thought I counted 22. Did I count wrong? 1, 2, 3, 4, 5, 6. You caught something there, Arjun, didn't you? Okay. Yep, look, there it is right there, right? The thing is, the way that this works, the way that this goes through is it just gets the next word every time, right? The next text every time. It doesn't care if it's in a comment or part of a main line. So here's my question. I counted 22, but I see what? I see 3 additional here. 1, 2, 3. Shouldn't it be 25? Why is it 24 and not 25? Which one of these? Good job, Rajat. Yep. When it gets in that next set of text, it's getting in all of these characters, and because this is not the same as, like you're saying, it's not the same as this, right? Exactly. Perfect. Y'all caught it. Good. Okay. All right. All right. So what we'll do is we'll take a little break here, and maybe we'll come back immediately immediately after this and talk a little bit about this count occurrences, because we want to be able to also not just count the number of words, but maybe have an idea of how many times like the word good appears in a sentence, how many times different words appear. Okay. All right. So we'll look at that right after the break. You know what? Actually, yeah. Okay. Let's take a break. We'll look at that right after the break and then get on into the slides for today. All right. All right. See you guys in 10 minutes. We'll come back at 2:29.